Hi everyone, how are you doing? Hope you are doing well. This is me coming back again after a long period of nothing, and this series is going to be a totally different style than the previous one. We are not focusing only on coding. Before jumping into the today's content or today's tutorial, I'm trying to make things clear here. I study by myself certain concepts or certain topics in petroleum engineering or reservoir engineering. I try to study and dig deeper so I can understand these topics and try to summarize them and explain them into these types of records that you see here. So this is actually the final step of my own learning process. This forces me to truly understand the concept before I can actually explain it to you. And by creating and sharing these videos, I am able to solidify my knowledge while hopefully trying to make complex things clear for you to understand or to make it easier. Without further ado, let's go to our today's tutorial, which is about the skin factor. In today's video, we are going to talk about what is a skin factor, like from the ideal Darcy law into introducing the skin factor in it. We will represent the skin factor mathematically into the Darcy law, and we will talk in some sort of details about types of a skin factor, and in brief, how the skin factor is measured in the actual field. We will write very simple Python code. You know, I love Python, and so we'll write a very simple Python code like to model the concepts or to model the reservoir well system and so on. It will be pretty easy. You will not find it hard to follow along with this code. So now, what is the skin factor? The skin factor is firstly introduced by Van Everdingen and Hurst. I can read this for you and you will actually get nothing from it. So it's a dimensionless numerical value used to analytically model the difference in the pressure drop observed in the actual producing oil well compared to the pressure drop predicted by Darcy law for the ideal well. What this means? Simply, if we have this reservoir well model, by Darcy law, we expect this type of pressure drop, like from BE to BWF. But in the actual field, the drop is higher, and so the actual BWF is lower than the BWF predicted by Darcy law. So they try to capture this behavior into an abstraction, which is called the skin factor. So the skin factor is abstraction, simplifying the complex three-dimensional flow problem into a single one-dimensional pressure drop loss that can be easily integrated and into standard production equations. So it is simply an abstraction that capture any pressure drop additional to the one that is expected from the Darcy law. We all know Darcy law, like we all know this equation, Q equal to K times H times PE minus PWF over 141.2 mu ln RE over RW. We all know this equation, and 141.2 because we are dealing with the field units. This equation is for the steady state. The assumptions of this equation that we have a steady state flow regime, like constant reservoir pressure at the outer radius. We have single phase incompressible fluid. We have radial flow and all the assumptions of Darcy law. So we have this reservoir that is circular, and we have the wellbore centered exactly in the center of the reservoir. If we talk a cross section like this, this will be our model. Okay, so we have here is the RW, here is RE, which is the reservoir radius, and this is RW. which is the wellbore radius. And the expected pressure inside the reservoir is going to be like this. We are going from PE, which is the reservoir pressure, into PWF. So the assumptions of this ideal system is that we have homogeneous reservoir, we are in the steady state flow regime, we have single phase incompressible fluid, we have vertical well, it must be vertical well that fully penetrates the reservoir, there is no partial penetration and these types of non-ideal behavior. So we have all the system in the ideal behavior. Let's jump into the code and try to model and to actually visualize the pressure distribution inside this system. It will be pretty easy. So here is the code. Inside this cell, I'm going to import numpy matplotlib, and this is my own style for the dark theme visualization. And I will run this cell. And those are the parameters that define our system. So we have a uniform, or we have homogeneous reservoir with a permeability of 150. The reservoir thickness is 50 feet. The reservoir pressure at the boundary is 2500. The BWF is 1800. We have the viscosity, the RE, the RW. We have the well that is vertical and fully penetrating the reservoir. And so we can write our own function for Darcy, like solving Darcy for Q, like to get the expected Q from this system. So we can write Darcy Q, like solving for Q. We need K, H, PE, BWF, mu, RE, and RW. Okay, we will return K times H times PE minus BWF over divided by 141.2 times mu times mb.log, which is simply ln. mb.log is log to the base e, and so it is ln re over rw. And this will be our Darcy law solving for Q. So I will call this function with the system parameters that we have here. We have the K, which is this K. We have the H. We have the BE, the BWF, the mu, the RE, and the RW. And let's print the Q. So the expected Q from this system is going to be 2937 reservoir barrels, because we didn't divide Q by the formation volume factor, so we are dealing with the reservoir barrels. This is simply solving Q, Darcy law for Q. We can actually visualize the pressure distribution from RW to RE by coming back to the slides. We have this equation. We can simply copy it here. So this tells us that the pressure at any radius is going to be the BWF plus Q times mu over 2 pi KH, 2 pi because we are working with the system units, times ln R over RW. Let's define the points that we will estimate the pressure at, which is going to be the radius point. I'm going to create an array mb.len space from RW to RE. So the first point of the array is going to be RW and the last point is going to be RE. And I need 1000 point of equally spaced, 1000 equally spaced point from RW into RE. If we printed the first value of this array is going to be the RW, and the last value is going to be the reservoir radius. Okay, and now let's type the function to calculate the pressure at these points. So the BRs is going to be BWF that we have, plus, and now because you are working with the field units, it's going to be 141.2 times Q that we solve in the system for, this Q, times mu okay, times mb.log drs over rw. This is divided by k times h. If we printed brs 1 0 and brs, the first and the last value, the first value need to be the bwf and the last value need to be the reservoir pressure. We have bwf as a scalar value, we have q mu as a scalar value, we have kh as a scalar value. So where this array came from, brs is an array. So where this array came from, we have the rs as an array that we defined here. So because we are using numpy in this equation, so it will apply this equation into each value inside the rs array. So we have the brs is an array that result from applying this equation into each value inside the rs. And now we have the radius from rw to re and the expected pressure. We can plot this, the r's and the pr's. The label is going to be the reservoir pressure, and the plot is going to be like this. So we are starting with rw with the bwf pressure and ending with the reservoir pressure with the outer radius. Some people will misinterpret this plot, expecting that the pressure drop here, which seems to be large, is by the skin factor. Here we didn't introduce any skin factor. We are working with the ideal system behavior. So if we plotted this on semi-log scale, semi-log x, so this is going to be a linear plot or a line between the log of the r from this equation. We have ln r and br as a line if we plotted the rw on the log scale. So this is simply trying to model this ideal behavior using a pretty basic code. Now let's come back to the slides. So for now, we are dealing with the ideal behavior without introducing any damage in the near wellbore area. Now we will introduce this damage. So we have this equation, just for remembering, 2 by kh pe minus pwf over mu ln re over rw. So this is the ideal Darcy law. And now, by any type of operation or anything that caused a physical change in the rock properties like the permeability, there will be a damage in the near wellbore area, which is this area. So this area is going to have another permeability than the actual formation permeability. So we will use K as the actual reservoir permeability and Ks as the altered permeability caused by any operation, representing the damage or the enhancement. And we have the reservoir radius. Let's erase this line. We have the reservoir radius. We have the radius of this altered zone, and we have the RW, the wellbore radius. So here we actually going to have two pressure drops, two distinct pressure drop. The first pressure drop we will denote this as PS and this as PE. So the first pressure drop is going to be from PE to PS, and the second pressure drop sorry for this, and the second pressure drop is going to be from BS to BWF. So BE minus BWF is going to be BE minus BS plus BS minus BWF. Let's try to simplify these terms. So BE minus BS is going to be Q mu over 2 by K, which is the actual reservoir permeability, H ln RE over RS. And BS minus BWF is going to be Q mu over 2 by KS, which is the altered permeability, H times ln RS over RW. And now we will substitute this into this equation. So PE minus BWF is going to be Q mu over 2 by KH ln RE over RS plus Q mu over 2 by KS H ln RS over RW. And by taking the common operator, the common factor, so BE minus BWF is going to be Q mu over 2 by H 1 over K times ln RE over RS plus 1 over KS ln RS over RW. By reformatting this equation to be into the equations that we know about Darcy, so Q is going to be 2 by H PE minus PWF over ln RE over RS times 1 over K plus ln RS over RW times 1 over KS. We can actually multiply by K both in the upper and the lower side to make it more like Darcy law. So Q is going to be 2 by KH PE minus PWF over ln RE over RS plus K over KS ln RS over RW. So this will be our final equation. Let's try to summarize it here. Q equal to 2 by KH PE minus PWF ln RE over RS plus K over KS ln RS over RW. And Darcy equation is like this: 2 by KH PE minus PWF mu, there is mu here that I forgot, ln RE over RW. Now, can we actually manipulate these terms to introduce ln RE over RW to be more like the ideal Darcy equation plus something? So the denominator to be ln mu ln RE over RW plus something, and this something is going to be the representation of the additional pressure drop into the system due to the altered zone. So it will be the idle behavior plus something, and this, the plus something, is going to be our representation of the skin factor. So we can manipulate this actually mathematically. So we will take this part, which is ln RE over RS plus K over KS ln RS over RW we can make this simple adjustment. Add len rs over rw and subtract len rs over rw. It is like we did nothing. We added and subtracted the same term. But by combining these two terms together to be len re over rs plus len rs over rw plus k over ks len rs over rw minus len rs over rw. We all know that len x plus len y equal to len x times y. This is the logarithm's laws. So this can be len re over rs times rs over rw. And now the rs will disappear and we have len re over rw. And for this section, it is going to be, we will take the common term rs over rw, k over ks minus 1. And now we have simplified this term to be in this form. So the final equation is going to be q equal to 2 by kh be minus bwf over mu len re over rw plus len rs over rw times k over ks minus 1. And voila, by comparing this equation into the ideal Darcy equation, we have this added term, which now can be simplified to be S. So S is len rs over rw times k over ks minus 1. And this is ks and this is k. So if ks is lower than k, so we have damage. And this term will be positive, and so the skin factor will be positive. So positive means there is damage because Ks, which is the permeability of the altered zone, is lower than the actual reservoir permeability. And if Ks is larger than K or higher than K, this term will be negative. And so the skin factor will be negative. And so we have enhancement in the altered zone compared to the actual reservoir permeability. And if K is equal K, this term will be 0, and so the skin will be 0. And now we have gone from the ideal Darcy law into introducing the altered zone and the mathematical derivation of the skin factor, which is the abstraction of the additional pressure drop due to the change or the alteration. It can be actually physically or non-physical, but let's simplify the alteration in the near wellbore zone. This is the part 1 of our today's video. We will continue by the types of the skin factors and how it is measured. Let's continue with the second part of today's tutorial. And let's talk about the taxonomy of the skin factor. Simply the classifications of different components of the skin factor. The total skin factor measured in the well test is a composite value. It is the sum of several different effects. Like the total skin factor can be actually divided into two main components. The real skin factor and the pseudo skin factor. The real skin and the pseudo skin. What is the real skin? The real skin is caused by an actual physical alteration or physical change in the formation permeability near the wellbore area. Either it is damage or stimulation. So there is physically change of the rock properties, which is in our case the permeability. But the pseudo-skin caused by alteration or change in the geometry between the reservoir and the well, or different change in the flow conditions. So caused by geometric or flow conditions that can add pressure drop or can actually reduce the pressure drop in certain cases. But simply the pseudo-skin, no change in the physical properties of the rock. The real skin actually change in the physical properties. Understanding actually the components of the skin factor is critical for choosing the right treatment. And we will see an example of this, like an imaginary example. The skin factor, which now we will talk about the real skin factor that can cause damage to the formation, meaning a positive skin. We have the drilling and completion fluid invasion. The mud solids and the cement physically plugs the bore throats inside the reservoir, like the liquid filtrate invades the rock and can cause harmful chemical reaction inside the throats. This happened during the drilling or the completion. This formation damage or the skin can happen at any point in the well's life and can caused by several mechanisms. One of them is the drilling and completion fluid invasion. The second one can be the clay swelling. Simply the fresh water or a low salinity filtrate react with the clay inside the bore throats, causing it to swell and so choking the permeability or reducing the permeability of the reservoir. The third mechanism can be the fine migration, which is the small or loose particles, which is silica or clays inside the bore throats and causing blockage of the flow and so reducing the permeability of the reservoir. Other mechanisms like the wax or the asphaltene precipitation inside the wellbore area or the scale deposition if we have incompatible reservoir fluid with the fluid introduced into the wellbore, or the mechanical rock crushing like from the perforation. The perforation actually caused crushing for a certain zone inside the reservoir, causing a positive skin into this crushed zone. And the real skin can actually cause enhancement in the reservoir. We talked about the positive skin cases that cause damage to the reservoir, but now we will talk about cases that can cause enhancement or stimulation for the well. We have the hydraulic fracturing, injecting the high pressure fluid into the reservoir to create fractures. These fractures acts as a highway, super highway for the hydrocarbon, like tunnels from the reservoir into the well bores directly, causing a negative skin factor, which means enhancement in the reservoir well productivity. Acid matrix stimulation, injecting acid like the HCl into carbonate formation, limestone, dolomite. The acid dissolves the rock and any damaging material, creating a new high permeability channels. This actually create negative skin. It can convert or turn a high positive skin into a negative skin case. This is for the real skin, that is the physically change of the reservoir properties. And now for the pseudo-skins. We talked about the pseudo-skin as the pseudo-skin components are the pressure drops that are not caused by permeability change or physical change. One example is the partial penetration. What is the cause? Here in this plot, we have the well fully penetrating the reservoir, and so the flow of the fluid from the reservoir into the well bore is smooth. But here in this case, we only perforated certain zone inside our bay zone or inside the reservoir. This causes the flow path of the fluid to converge and squeeze near the wellbore area, causing additional pressure drop. And so the cause is the partial penetration, the effect is the convergence or the squeeze into a smaller entry area between the reservoir to the well, causing extra pressure drop. The result, we will have positive pseudo-skin. Another case, which is the wellbore inclination. The ideal behavior we talked about is the well is vertical and fully penetrating the reservoir. In certain cases, we will have deviated well or a horizontal well. So the cause of this mechanism is we have an inclination angle between of the well. So we have a deviated or simply horizontal well. The effect actually, we will have a larger entry area for the flow from the reservoir to the well. We will have more contact area between the wellbore and the reservoir. In this case, actually, the pressure drop will be reduced. This causes an enhancement in the well productivity and so negative pseudo-skin. For the last part or the last mechanism, we can have non-Darcy or turbulent flow, which means we can have high velocity in the near wellbore area because we are like producing with high flow rate, and this is actually typical for the gas reservoirs producing in a high flow rate, causing the flow convergence from not convergence, like the flow change from laminar to turbulent flow. The laminar is more smooth flow and the turbulent flow can cause or will cause extra pressure drop, and this additional pressure drop is not a fixed number. So the turbulent flow cause additional pressure drop that is actually rate dependent on the rate on which the fluid flow. The result, we will have a positive skin. Why the classification is actually important? Why we need to discriminate or to know the components of the total skin that we measure from the well test. Let's imagine this scenario. It is imaginary case, but this happened on the actual field. We have a well that is show that we have a total skin of positive 10. You can make your assumption, which is in this case incorrect, that the well is damaged. Let's do an acid job or let's do hydraulic fracturing. But the reality, this positive 10 skin is actually 80% from the partial penetration and only 20% from the damage. So the major problem here is the partial penetration. By taking the action of doing acid or hydraulic fracturing, will be a costly failure because it doesn't fix the problem, and it is additional costs. The correct action is to do work over to add more perforations. So in conclusion, the cause of the skin is more important than the value itself. What is the economic impact or how we can use actually the skin into our management strategy? It can be used for candidate selection. Imagine a case if you have a well with a skin factor of plus 20. This is a red flag. We all know this. But this actually can be a huge opportunity. If you solve this problem and reduce the skin factor of this well, it can dramatically increase the production from this well. So it can be used to identify a well that is a prime candidate for a workover. Evaluating the success of any treatment, like if we know the skin factor before the treatment, either it is acid or hydraulic fracturing or a chemical treatment or anything, and we know or we measure the skin after this treatment, we can quantitatively measure how successfully the job was. Forecasting, like the skin factor is used in any model, either it is well model, simple well model like in Prosper or pipe sim or for reservoir stimulation. So getting the right or the actual skin factor is to be more accurate. Getting the right value of the skin factor will make it easier to get accurate prediction for the future. The life cycle can be summarized by this. You test your well, and then based on the results, you can do a diagnosis to know the reason for this skin, and then you do the treatment. After the treatment, you remeasure or retest the well again to assess the or evaluating the success of the treatment, and then you will update your model of the new skin factors. The plot twist of this tutorial is that I will not actually talk about how the skin factor is going to be measured. It is your part to search how it is measured. Simply any PTA, pressure transient analysis, or other advanced techniques that can be used to model the well or the reservoir in any softwares and so on. So this will be your part of this tutorial. This is the end of today's video. Hope to see you again soon.